students. So today we will discussing about the plane waves or normal incidents, okay, or a reflection of plane waves at normal incidents. Actually, we have the two incident waves. Okay, then let's see here. We have the two incidents. Uh, First, we will see the difference between the two incidents. Suppose if incidents normally to the surface, that is along normal ray, then it makes a zero angle with the normal, and this is known as the normal incidence of light on the point of incidence. For suppose if incidence ray makes any other than 0 degrees, then the angle of incidence is known as the oblique angle. But in this class we are going to discussing about the normal incidence, which means it makes a zero angle between the transmitter and incident ray. Okay, let's see how you can propagate the plane wave at normal incidence. For suppose if you observe here, when a plane wave propagates from one medium to other medium, okay, for suppose the wave propagate one medium meets a different medium, it is partially reflected and partially transmitted. How partially reflected and how partially transmitted? Let's see, this is our medium at normal incidence. Here we can propagate our incident wave in this direction. Then due to this medium dispersion, the something signal may be partially reflected and something signal may be partially transmitted. How we will observe here. The media is especially dispersive media in which some parameters already you know. Whenever you can choose the some media, it has a something characteristics. We have something characteristic nothing but permittivity, permeability and intrinsic impedance. But here you can choose in some parameters. Permittivity affects the propagation which varies with the frequency, then here we can choose the medium. We have considered uniform plane waves traveling in unbounded medium. Okay, here unbounded is nothing but actually we have the two types of mediums. We have unbounded and bounded. Already you know, unbounded is nothing but here you have the something channel to propagate our signal. Okay, then we will see in next unit bounded medium. Bounded nothing but here we choose the some free space to propagating the waves. Okay, but suppose if you observe in this slide, the media is especially dispersive media in which some parameters are effects of propagation which varies with the frequency. Due to this effect of effects, some partially reflected and partially transmitted a wave through this medium 1 to medium 2. Okay, for suppose if you observe here, the effect of dispersion media on a signal, effect of dispersion on medium. Okay, if you observe here, the signal envelopes will change in a shape as it is propagates, so that the detection and faithful representation of the original signal at the receiving end become problematic. Okay, here what you observe here, it effect of dispersive media. But suppose if you have the some dispersive media in between the two mediums, due to this dispersion media, some signal may be propagated and some signal may be reflected from medium 1 to medium 2. Okay, then what are the effects we have on it? Here you can observe the signal envelope will changes in a shape as it propagates, so that detection and faithful representation of the original signal at the receiving end become problematic. The receiver have some problems to get the original signal due to this dispersion media. This is the one of the problem due to the dispersion media. So the dispersion and attenuation must both be evaluated when establishing the maximum allowable transmission distances. Okay, Here you can observe the both dispersion and attenuation must both be evaluated when establishing the maximum allowable transmission distance. These are the two effects we have from this dispersion media. Then reflection of uniform plane waves at normal instance. Whenever you can choose the normal instance, the angle may be 0 between the incident and transmitted wave. For suppose if you observe, this is the geometry. Here you have the two axes visible. One axis is non-visible, that is y axis. Here you have the x axis and z axis. Why you choose these two axes means the here you can assume the or wave propagate. Assume the wave propagate in between the two axes, that is z and x axis. The wave propagate between the x and z axes. That's why we can have visible these two axes. Other one is y axis. Already we know the uniform plane wave is nothing but our EM wave. EM wave is nothing but electromagnetic wave. It is a combination of both electric and magnetic signal. If you observe here, this is the here we have observed we have the two mediums, medium 1 and medium 2. The medium 1 has the these are the characteristics mu1 epsilon 1 dash epsilon 1 double dash. Here medium 2 has the characteristics mu2, I mean permeability, this is the permittivity, E2 dash E2 double dash. Okay, here you can represent the incident wave as plus sign, reflected represented as minus sign, and transmitted signal represented as 2 plus. 1 plus is nothing more from these two are the medium 1, this is the from medium 2 we have. If you observe, this is the instant wave propagated from medium 1 to medium 2. Okay, as I told, the wave propagate in between the x and z axis. Okay, we can represent the our electric signal like this. E1 plus nothing but this is instant wave. E1 means from medium 1. If you observe, this is the geometry. In the medium 1 we have the two waves. One is the instant wave, other one is reflected wave. Always in a medium 1 we have these two signals, reflected and instant signal. In medium 2 we have only a transmitted signal. Okay, due to this medium dispersion, our wave instant wave is partially reflected and partially transmitted and partially reflected as we propagate the signal through this medium. Okay, then now we can represent the instant waves. E1 plus, already I told, instant wave represented the plus sign, reflected represent the minus sign, transmitted represent the plus sign, but in medium 2. Okay, here as per this diagram we can observe here. Okay, the electric wave polarized in x direction. Okay, then magnetic signal polarized in y direction. Here we observe you have the dot in circle, which means the out direction. As per Fleming right hand rule, we can decide the directions of wave polarizations. Okay, electric signal polarized in x direction, the magnetic signal polarized in y direction. Okay, the overall EM signal polarized in z direction. Here we can observe the z direction in terms of k. Okay, this is the direction of our instant wave propagation due to the dispersion medium, partially transmitted and partially reflected. Here the reflected signal represented like this: E1 dash, E1 minus, H1 minus. This is the reflected magnetic signal, this is a reflected electric signal. Here if you observe, this is the direction of your reflected signal. That's why you can observe here the cross in a circle, means inward direction. And then if you observe, in a medium 2 we have the transmitted signal E2 plus and H2 plus. Here also we have the outward direction as per our Fleming right hand rule, and the propagation of wave is in z direction. This is the direction of z. In at normal instant, as I already told, at normal instant the z equals to 0. Z equals to 0 here. As I told, the plane wave propagating along the z direction is instant normally on the boundary z equals to 0 between the medium 1, characterized by this characteristics, and the medium 2 characterized by these characteristics. Here also we have the sigma 2, and here also we have the sigma 1, I mean conductivity. Okay, in a figure subscripts 1 plus 1 minus T denotes the incident, reflected and transmitted waves respectively. The incident, reflected and transmitted waves are shown in this geometry. Okay, then the Poynting vector means here from this we can measure the power, keeping this keep as a note, then we will discuss in later. Now this is the direction of your propagation. Okay, the electric signals are propagated in x direction, magnetic signals are propagated in y direction, then the overall EM signal propagated in z direction with the help of cross product. Then if you observe, there is a definition of normal incidence. Already we seen the difference between the normal incident and oblique incident in first slide. The wave propagation direction is perpendicular to the boundary surface. But suppose if you observe the wave propagation at oblique incidence, the wave propagation direction is not perpendicular to the boundary surface. If you observe here in a next slide. Okay, already we've seen these all things. Incident waves. Okay, now we can represent the incident wave in terms of electric and magnetic. Okay, here E signal and H signal is traveling along the z direction in a medium 1 and linearly polarized in x along the x direction. Then it is represented like this: Ex1 means E polarized in x direction from medium 1 plus is nothing but incident waves. Already I told in the previous sections or previous classes, the electric signals is the EM signals are represented in terms of space and time. That's why you can use the Z and T. Z is nothing but space, T is nothing but time, space and time. Okay, signal may be represented in terms of space and time. Then this is the your electric signal from our incident waves. Ex1 naught plus into e to the power of minus gamma z. Okay, na? Here why you can multiply by this time factor to assume that then this is the our signal, this is electric signal Ex1 naught plus e to the power of minus gamma z into e to the power of j omega t. Here j omega t, exponential of j omega t is nothing but multiply by the time factor. Why means here I want to get the real and imaginary terms from this. Then we need to multiply this time factor like this. Then here take the real parts from this instant waves. Ex1 plus z comma t equals to Ex1 naught plus e to the power of minus alpha. Here already you know the gamma equals to alpha plus j beta. This is the propagation constant equals to attenuation constant plus j beta. Here beta is nothing but a phase constant, attenuation constant and phase constant. Gamma is nothing but propagation constant. Then you can expand this gamma as alpha plus j beta. Then we have this equation. Okay, then take the real parts and imaginary parts. Then this is our real, this is our imaginary terms. Okay, okay, this exponential term represented in terms of cosine and sine terms. This equation looks like this. This equation looks like this, and the expansion of this one is we will observe in next slide. From this finally we have this equation for electrical signal. If we suppress the time factor, j omega t in a equation in a phasor form. Then finally we have, okay, as per your interest, as per your considerations, we can include the time factor. For suppose if you include the time factor, we have this equation. Then for suppose you can suppress the time factor of j omega t from above equation, I mean phasor equation, we have this terms only. This is our electrical signal, and this is our magnetic signal, magnetic signals. But how you can represent the magnetic signals here in terms of V only means we have the relation. This is the relation here, eta intrinsic impedance equals to E upon H. Okay, na? In terms of H, in terms of E, how we can represent the H like this: 1 by eta 1 into e to the power of, sorry, E x1 naught plus into e to the power of minus alpha 1 gamma 1 into Z. These are the two equations we have. Here if you observe here, n1 and gamma 1 are the complex unless sigma 1 equals to 0. Okay, na? This is the way we can represent the different waves from your different reflections at normal instance. Okay, shall we continue next class?